need to use some kind of trig function.
Mm-hmm. So which one would we use for AY? Did you ever do this? So, TOA.
No.
Oh, really? Yeah, you must have had a nerdy math teacher. So this is how I always remember it, and it's kind of dumb, SOCA TOA, but you'll hear a lot of people say it. So this means that the sine of an angle equals the opposite over the hypotenuse. The cosine of an angle equals the adjacent over the hypotenuse. So what do you think this one is?
Opposite over adjacent.
Yep.
Tangent.
So the tangent of an angle equals the opposite over adjacent.
So for AY, then it would be it would be cosine?
Yep. So we can say 9.8 times the cosine of 10 degrees. Because we know that the cosine of 10 degrees equals the adjacent, which is a sub y, over the hypotenuse, which is 9.8. So then you just rearrange it. You multiply 9.8 up and you get that. So about a sub x.
That would be sine.
Yep. So 9.8 sine of 10 degrees. And both of these are negative, right? Because our a sub y is going down, our sub x is going to the left. And you can even just leave in your negative 9.8 there, and it'll keep those signs going. Okay. So now we can draw these, right? We can say a sub y equals negative 9.8 cosine of 10 degrees. And a sub x equals negative 9.8 sine of 10 degrees.
Okay.
So which one do we want to use in our equations?
I think sine's usually easier to work with, but I don't know.
Right. But in terms of the accelerations, is he really going to be accelerating down into the ground?
No.
No. So this one actually doesn't even happen because the ground pushes back and keeps it from going down into the ground. So this is the one that we want to use. This is the component of acceleration pointing down that hill.
Okay.
So now we've got initial position, initial time, initial velocity. We've got final position and final time. We don't have these ones. We have a final velocity and we have the acceleration. So which one of these do we want to find that we're ultimately looking for?
The final position.
Yep. So what kind of equation can we use to find this one using what we already have?
Is it one of the kinematic equations that we were working with last time?
So you've got x final equals x initial plus v initial t plus 1/2 at squared. Or you've got v final equals v initial plus at. Or v final squared equals v initial squared plus 2a change in x.
So if we're looking for x, we'll probably use the first one.
Yep. So we're looking for this one. We've got this one. We've got that one. What about this?
We don't have time.
Okay, so maybe we don't want to use that one. But this one still has an x in it, right? This one doesn't have x in it at all, so that one's not worthwhile.
Yeah. Okay.
This one we could find the change in x, which is the same as that whole distance. We have acceleration.
Yeah, we have that too.
We have that.
Okay.
So let's use this one. So what's the final velocity?
That's gonna be 0. And that one's gonna be 900.
900 plus, then let's just plug in these numbers and you can just throw it in your calculator. So negative 9.8 sine of 10 degrees delta x.
Okay.
So what is delta x going to be equal to without doing any more calculations? Just rearrange it.
Okay, it's gonna equal negative 900 plus 2 times negative 9.810.
So when you subtract your negative 900 over, then you have
Oh,
negative
you
900
divide by it.
equals. Yeah.
Okay.
Divide by, divide by 2 times negative 9.8 sine of 10 degrees. That'll leave you just with this on the other side.
Okay.
And luckily, because you have a negative acceleration, you know that that's going to cancel out with that. And you end up with a positive.
Yes.
Because if you ended up with a negative, so say you forgot your sign on your acceleration, in the end your answer would be negative. You'd say, wait a minute, I know that he didn't start at 30 meters per second and then roll down the hill until he stopped and then start rolling back up. You know, you can just recognize that. So this would be your answer. It's, I don't know what the sine of 10 is, so I'm not going to do it in my head.
Let's just say that it comes out to be like 50 feet or something, or 50 meters.
Okay.
And that would be the change in x.
Yes.
Would that be equal to x final?
Yeah, so let's talk about that.
Because x final is just x final, or no, x, the second one minus the first one, right?
Right, so you can just say delta x is whatever your final x is, x1 minus whatever your initial x is. So in this case, because initial is 0, you're right, your delta x is going to be equal to x1.
Okay.
But if, say that there's some other motion before here, you had, maybe you rolled, like he was driving up the hill for a little while with a certain acceleration and you had an x not over here, and then this was x1, and this is x2, and you eventually found out that, say, this is 75 meters. So if this was 75 meters that he's already gone up the hill, and your delta x ended up being 50 meters, what would be the high, like how far would he have gone up the hill total?
Well, just 50 plus 75?
Yeah, so in that case, you have to remember that you've got this little equation, so you'd say delta x equals x2 minus x1, which we could replace with 75. And you'd be able to say, okay, 50 equals x2 minus 75, x2 equals 125 meters.
Okay. I think the one thing that, because I understand the kinematic equation part,
Mhm.
but I wouldn't, if I saw this problem, I wouldn't do that.
You wouldn't turn it.
No, I wouldn't know how to do the triangle thing that you did.
Okay. Well, you'll get a lot of practice doing it because you do it all the time.
Okay.
So,
All right.
so you'll see a lot of times where you'll be able to use this because, I mean, that's kind of how it works in physics. You have these two dimensions that we're always in. As long as, say, even if you're throwing a ball, like you throw a ball and that's in 3D, right? You're throwing it and it's covering some X and Y and Z, but it'll, in general, cover a path that kind of looks like this, right?
Uh-huh.
So we can just change it into two-dimensional motion, but then we still have to break it down into X and Y components. So every problem that you'll work, you're going to be taking something that's in 2 dimensions and say, well, I don't really want to work with it in 2 dimensions. Let's break it down into its X and Y, make it 1 dimension.